What do you guys remember about the area under the curve? How do we find that? What does that mean? Okay, so let's think you just had some random curve. It started, my normal curve that I go with here. Starts at A, goes to B, from A to B. How do I find the area underneath that, knowing that this thing is represented by f of x? To find that, we are going to use the definite integral from A to B of f of x dx, and we know that the answer to this, using the first fundamental theorem of calculus, said capital F of B minus capital F of A will give us the area between these 2 points. So that's just how you find the area under a single curve. Today's notes, we're going to talk about what happens between the area between 2 curves. So this is, I believe, 6.1 in your textbook for those of you who are following along. So the title of today's notes are 6.1 area between 2 curves. So let's start real quick with a simple one here. Find the area of the region bounded by the x-axis and y equals x squared plus 3 on the interval from 1 to 3. Oh, this is just a real quick proof that you know how to find the area of just one curve. So this would be from 1 to 3 x squared plus 3 dx. So x cubed over 3 plus 3x from 1 to 3. I would plug in 3. So 3 cubed over 3 plus 3 times 3 minus 1 cubed over 3 plus 3 times 1. And so then you end up with 9 plus 9 minus 1/3 plus 3. And this is going to end up with, so 9 plus 9 minus 10/3, so 44/3. Okay? Essentially here there was really only one curve. But if you wanted to think about this, x squared plus 3, 1, 2, 3, looks like this. You are graphing it from 1 to 3. Essentially, the 2 curves here, I mean, I know we think of it just this area right here, that's only one curve, but you could also think of this, when we say the x-axis, this is the curve y equals 0. Okay, so the top curve is x squared plus 3, but the bottom curve is y equals 0, which is just our x-axis. So I found the area between those 2 curves. It's just that here when y is equal to 0, I would have a 0 in my equation, and that would just be silly. So some of you are like, wait, in the equation, what are you talking about? Let's try a different one. Let's talk about the area bounded by the x-axis in the function y equals negative x minus 2 squared plus 4. So let's graph that one. So this is a quadratic in vertex form with the center, a vertex at 2, 4. So 1, 2, 1, 2, 3, 4. And then it's going down. There's no dilation, so over 1, down 1. Over 2, down 1, 2, 3, 4, over 2, 1, 2, 3, 4. So I want to find the area bounded by the x-axis and this curve. So I really only need, and by the x-axis here, so I just need this space right here. Well, notice this one worked out really nicely, that it crossed the x-axis at 0 and 4. I could figure that out by just setting this equal to 0 as well and solving, but I could tell from graphing this one that one worked out really, really well. Okay, so my bounds for this are going to be from 0 to 4, negative x minus 2 squared plus 4 dx. Okay. For this one, you could we do a u sub? U sub would be silly. It's just a quadratic. Let's just go ahead and multiply this one out here. So the integral from 0 to 4 of negative x squared minus 4x plus 4 dx. Let's go ahead and distribute that negative and make that negative x squared plus 4x minus 4 plus 4 dx. So those two cancel out. Okay, so I have the antiderivative of negative x squared plus 4x. So this is negative x cubed over 3 plus 2x squared from 0 to 4. Plug this in. I've got negative 4 cubed over 3 plus 2 times 4 squared minus, here I know when I plug in a 0 I'm going to get 0. Please still show that you plugged it in to get the 0. Don't just leave off the 0 here altogether, because that's going to be improper math. You want to show that you at least plugged it in and got 0. So 4 cubed over 3, so negative 64 over 3 plus, what is that? 16 times 2 plus 32. So 32, that would be over 3, so this would be 96 over 3, right? Because 32 times 3, yeah. So 96 minus 64, so this is going to be, oops, come on, 32 over 3. So that is the area under the curve here. Again, top curve was the quadratic, bottom curve, x-axis. Again, still not so shabby. Okay. Now, what if we had two distinct curves and wanted the area between them? Well, we kind of have already done that, but let's tweak it a little bit here. Now the curve is y equals 3 and y equals x minus 2 squared plus 1. So now the curve, one of the curves is no longer the x-axis. Now that's been shifted up to here. Okay, so here's the line y equals 3. And then x minus 2 squared plus 1, another quadratic where the vertex is at 2, 1. And so over 1, up 1, boom, boom. And then over 2, up 1, 2, 3, 4. Ooh, my bounds aren't going to be as easy to find here, but we'll make it work. Okay, so this is the actual curve itself, but I only want this area right here. Okay, so to do this, first of all, we need to figure out, well, where should I start? From where to where? Okay, well, I know this is my lower bound, this is my upper bound. How do I find those points? How do I solve for any points of intersection? I find out where these two things cross. So where is x minus 2 squared plus 1 equal to 3? So x minus 2 squared equals 2. I take the square root of both sides. X minus 2 equals plus or minus root 2. And so then I add 2. So x is equal to 2 plus and minus root 2. So this guy is going to be 2 minus root 2. Whereas this one is 2 plus root 2. So I have my bounds. I know where I want to start and stop my integral. But now I need to figure out, well, how do I get this area? Okay, so remember, if I were to integrate y equals 3 from here to here, that's going to find the area of everything from here down. So that's going to find, for the curve y equals 3, that would find everything from that curve all the way down to the x-axis. Okay, that's what it would find. It would give me all of this area. Okay, the question is, do I want all of that? The answer is no. I don't want this extra stuff right here. I just want this overlap. So, but I at least need to start with that. So I'm going to have 2 minus root 2, 2 plus root 2 of just the curve 3. That's going to give me this rectangle here. Now, I need to take out all of, here, let me change it the color. I need to take out all of this stuff right here somehow. Or I guess I could just erase it. I need to literally not have all of this area. I don't want that area. Question is, how do I do that? How do I just erase that? Well, the answer is, if we look at this, okay, if I were to find the area under the curve of my quadratic, that would give me everything of the quadratic to the x-axis. So that would be all of this extra stuff that I technically don't want. So what I do is I simply subtract the area using the same bounds of my function negative, no, this one wasn't negative, of x minus 2 squared plus 1 dx, okay? Let's recap that real quickly here. If you find the area of just the line y equals 3, it goes all the way to the x-axis, okay? If you find the area under the curve, it goes all the way to the x-axis. So what you do here is you subtract the two, because then it takes out that overlap and you're left with just this part that you want right here. Okay, now the bounds are a little bit gross for this one. We could clean this up here. We could make this integral 2 minus root 2 to plus root 2 of 3 minus, this is a simple subtraction one here, so you know, I would have minus x minus 2 squared plus 1. Oh wait, I didn't distribute the 1, or distribute the negative to the 1. Boop, boop. Come on. Minus 1 dx. I'll give you a hint for this one. Even if you try to clean this up a little bit more, you would eventually plug this one into your calculator using Math 9, if you didn't already know that. Math 9 gives you an integral and you can plug in your bounds. I'll help you out here. The answer is going to be 3.771. Okay, that was kind of fast. Let's try, well actually let's kind of just, you know, generalize this here. So is there a way to write this process as a rule or a formula that we can use every single time? That should be 2 words, every space time. I just forgot to fix that. All right, a to b, f of x minus g of x, where f of x is greater than or equal to g of x for all x in a to b. All right, so when you have two functions, okay, if you want the area between two curves, you will subtract the two curves as long as you are subtracting the upper curve minus the lower curve, or the higher curve minus the lower curve. Like you could say a to b top curve minus bottom curve dx. Okay, or some people like to call higher, lower, top curve minus bottom curve. But either way, to find the area between two curves, so this is the formula for the area between two curves. You are simply going to subtract them as long as you subtract the top curve minus the bottom curve. Okay? Let's look at some examples here. So make sure we really understand this. So find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. This one, I kind of need a visual here. So let's graph this. So x squared plus 2, so 1, 2. Here's my quadratic. Okay. Y equals negative x, so that is a linear function with a slope of negative 1. Whoa, where did, oh, I went off the page a little bit. There we go. Boom. All right. X equals 0. When x equals 0, well, that's the y-axis. And x equals 1. X equals 1. Okay. So then I want all of this area here. Okay, now using the same rule that we just wrote down of top curve minus bottom curve, between 0 and 1, the top curve is this guy right here. Okay, now if I were to continue this on and on, there might be a place where they would have switched top and bottom the way I have it drawn. Maybe not the case, but maybe it could have. Okay, that does happen sometimes. We'll have to reevaluate when we get to those. Okay, so my bounds from 0 to 1. My top curve, so x squared plus 2, minus my bottom curve, negative x dx. Okay? So now I've got my integral, and now I just need to go ahead and solve it. So I'm going to have the integral from 0 to 1. Let's go ahead and clean this up. Make that x squared plus x plus 2 dx. I just rearranged the order so it's in our nice pretty, like, you know, degree countdown. You don't have to do that. This becomes x cubed over 3 plus x squared over 2 plus 2x from 0 to 1. So 1 cubed over 3 plus 1 squared over 2 plus 2 times 1 minus, here if I were to plug in 0, I get 0 for everything. So again, show that you got 0. 1/3 plus 1/2 plus 2, this is going to work out to be 17 over 6. So that is the area between these two curves from 0 to 1. Now, how is this different than previous problems that we looked at? Let's think about this. How was it different? Well, one way it's different, you have one curve above the x-axis, one curve below the x-axis. Our curves did not intersect here, okay? So in the past, to figure out where the bounds were, we found out where they intersected. Here, they don't intersect, so we can't do that, okay? So, yeah, that's a couple of differences there. We kind of had to use the information that they gave us for the bounds. So sometimes you have to find the bounds on your own by just where the intersection of your two equations. Other times they give you the bounds. So here they gave us the bounds. How lovely, how convenient. Let's keep going. The sine and cosine curves intersect infinitely many times, bounding regions of equal areas. Find the area of one of these regions. Ooh, fancy. Again, I really like to see graphs. So let's start with that. So here's the sine curve. And then I'll make the cosine curve another color. Oh, let's see if I can make that as nice. So here, I know I need to finish here. It's got to cross here. Here, I kind of have to like work this out here. So do. Oh, that's beautiful. Yeah, beautiful enough. Okay, this is y equals cosine x. Again, these two go on forever and ever. I don't really care though. I just need to know what is the area of one of those intersections. Oh, I tried to be smooth here. That right there. I want to find that area right there. Okay. Well, to do that, we need to figure out what are these coordinates. Where do they start and stop? Okay, so I need to find out what the bounds are by finding out where they intersect. So where is the sine of x equal to the cosine of x? Again, if I were to keep drawing this out, it would happen many, many times. But just the first places that they cross are going to be where x is equal to pi over 4 and 5 pi over 4. In our unit circle, they're in your first and third quadrants. Hopefully we remember this. Now, since I'm finding the area of just this curve right here, which curve is on top? Well, that looks like the sine curve with the cosine curve underneath. So my area is going to be from pi over 4 to 5 pi over 4 sine of x minus the cosine of x dx. Okay, so to continue this on from here, I just take the integral. The antiderivative of sine of x is going to be negative cosine x. Antiderivative of cosine is sine, so negative cosine x minus sine of x from pi over 4 to 5 pi over 4. I'm going to plug that in. So negative cosine 5 pi over 4 minus the sine of 5 pi over 4 minus negative cosine pi over 4 minus sine pi over 4. Let's see. So the cosine of 5 pi over 4 is negative root 2 over 2, but I already have a negative, so that's going to cancel it out. So that becomes positive root 2 over 2. And then minus, again, the sine of 5 pi over 4 is also a negative, but I'm subtracting it, so it becomes plus root 2 over 2 minus The cosine of pi over 4 is root 2 over 2, but I have a negative, so minus root 2 over 2. And then minus sine of pi over 4 is also root 2 over 2. Root 2 over 2 plus root 2 over 2 is just root 2 minus, well, negative root 2 over 2 minus root 2 over 2 is negative 2 root 2 over 2. So really just negative root 2. But it's a minus, that becomes positive root 2. So this all works out to be positive 2 root 2. So that is the area of just this piece right here. If I wanted to find the area of this curve right here, or of this intersection, okay, technically it would be the exact same area, but I would have to find it a different way. My bounds would be different. I would start at 5 pi over 4 and end at 7 pi over 4. And then I would also have to recognize that on this curve, cosine is above sine. So I'd say cosine x minus sine x. But in the end, you would get the exact same answer. Okay? So that leads me into my next question of what potential tricky situations could you anticipate? Well, the first one that I would anticipate are intervals where the top and bottom can change, okay? So kind of like the last situation, let's say we wanted to find the area of the first two pieces and pretend that this was a function where the first two pieces weren't identical, okay? In that situation, you have to swap the top functions, okay? So in that situation, you would have to split it up into multiple integrals. So that first tricky situation is where intervals where your top and bottom functions could switch, okay? Another tricky situation is if you have any asymptotes, perhaps. You can't actually, like, they're not continuous, so you couldn't actually integrate those up to the asymptote. You could get pretty close to it. Other tricky situations you might just kind of come up with on your own as we do some of these. So you want to just kind of leave some space here and see what tricky situations you think that you need to be worried about. Okay, let's do another practice problem here. Find the area between the graphs of f of x equals 3x cubed minus x squared and 10x, and g of x is equal to negative x squared plus 2x. Now, did they give you bounds? They did not. So that means you need to come up with them on your own. And to do that, okay, define the bounds. You find out where your functions intersect. So where is f of x equal to g of x? Okay, so I'm going to say, where is 3x cubed minus x squared minus 10x equal to negative x squared plus 2x? Let's see. So I'm going to add everything to the other side. Oh, well, luckily, boop. The negative x squareds cancel out. So I'm left with positive 3x cubed, and then minus 12x equals 0. I'm going to factor out a 3x. So 3x with x squared minus 4 equals 0. So then I've got 3x minus 2 x plus 2. So this intersects at x equals 0, 2, and negative 2. Okay, so if that's the case, so I'm going to have two separate integrals here. Okay, I'm going to have an integral from negative 2 to 0, and again from 0 to 2. Now, the question becomes, which is my top function and which is my bottom function? Well, I can't tell just by looking at these two equations. So what I have to do is I need to pick a point within both functions in between, like between negative 2 and 0 and between 0 and positive 2, and then go from there and see which one's higher or which one's lower. So again, I have my integral broken up. I know I'm going to say from negative 2 to 0 of something minus something else, plus the integral from 0 to 2, something minus something else. I don't know what these somethings are. Is this f and that's g, or is this g and that's f? I don't know. So to figure that out, I need to pick a point between negative 2 and 1. Let's go negative 1. F of negative 1 is 3 times negative 1 cubed minus negative 1 squared minus 10 times negative 1. Okay, this works out to be positive 6. All right, well, how does that compare to g of negative 1? G of negative 1 is going to be negative 1 squared plus 2 times negative 1, and that is equal to negative 3. Okay, so in my first interval, f of x is higher than g of x because when I plug in a random point, I chose negative 1 because it was simple. This number was higher than this. F of negative 1 was higher than g of negative 1. So that tells me in my first integral, I'm going to say f of x minus g of x. Okay, now I'm assuming that they swap here, but I don't know that for sure because I don't know what the graphs look like. So I need to pick a point between 0 and 2 to figure out, do I put f or do I put g first? Don't know. So let's check. What is f of 1? So 3 times 1 cubed minus 1 squared minus 10 times 1. This works out to be negative 8. And g of 1 is going to be negative of 1 squared plus 2 times 1. This is going to be positive 1. All right, now g of x, or g of 1, is higher than f of 1, so this is going to be g of x minus f of x. I didn't look at the graph, and I would not have known that without plugging in the numbers themselves, okay? So you have to do that before you integrate, okay? So now I've got the integral from negative 2 to 0 of f of x, which is 3x cubed minus x squared minus 10x, minus g of x, which is negative x squared plus 2x dx, plus the integral from 0 to 2. Now I want to swap the 2. Now I have the integral of g of x, so negative x squared plus 2x minus f of x, which is 3x cubed minus x squared minus 10x dx. From here, it's just a very basic integration from this step forward, where you're just going to distribute the negatives and then use first fundamental theorem. We've done this so many times that I'm actually going to skip over that in this video for the sake of time. But from here, you might want to pause it, go ahead and work it out, and then make sure you get the exact same thing that I've got posted on Canvas. Actually, I'll tell you the answer is 24. Okay, cool. Make sure you get that. Moving on. All right, now to find this using a calculator, okay, what you want to do here, okay, we want the area from negative 1 to 1 between 1/2 x squared plus 1 and 2x cubed plus 2. Now careful here, 1/2 is a constant. This is not 1 over 2x, 1 divided by 2x squared. This is 1/2 times x squared. You could actually type this in your calculator just like this. That's why I copy and pasted it. So when we say use your calculator, okay, be very careful because here's what's happening. Here's negative 1, and I want you to go to positive 1. Here's positive 1. Okay, so I'm going to find the area of this curve, but also the area of this curve. But this is another one of those tricky situations where what do you notice? What happened when you go from negative 1 to positive 1? You have, you have it to where it swaps, it switches. So let me show you how you would type this in your calculator. All right, so I've got my calculator pulled up and I'm in my y equals window. Okay, so my two functions that I have here, is it not going to let me do this? Hang on. Oh, I need to, hang on. 1 second. I got this. Maybe. Okay, no, we're good. All right, I don't want alpha. All right, so I'm going to type in, I can't move this around and show you the other two curves, maybe. I don't understand. Okay, well, I know what they are. Okay, so your two curves were 1/2 x squared plus 1. So 1/2 x squared plus, nope, not 2, plus 1. And then I have 2x cubed plus 2, 2x cubed plus 2. Ooh, no. Oh, man. plus 2. Okay, so 2x cubed plus 2. So again, these switch places, okay? If I go to my, let's just go to Zoom 4. That should, there's the first one. All right, so there's the other curve. So again, we said that they swapped between the top and the bottom curve. So go back to your home screen, okay? Oh, you can ignore all that stuff. So what we're going to do, your calculator can help account for that for you. So go to Math 9. We wanted our bounds. Actually, our bounds are from -1 to 1, so -1 to 1. Now, we said that the bounds swapped, right? So if you wanted to, we could find out where they intersected and break this up into 2 separate integrals, but I want to be a little bit more efficient here and get it all done at once since I'm using my calculator anyway. I'm going to put absolute value bars right here. So you're going to click Math, arrow over to Number. The first option is ABS for absolute value. You're going to say y1 minus y2. To click y1, click alpha, trace, y1 minus alpha trace y2. When you do it like this, your calculator automatically accounts for the swap between the top and the bottom curve. Okay, it does that for you by finding the absolute value of it. Click enter, and you should get an answer of 2.047. Okay? So that's how you type that in your calculator. Now, if you were doing this by hand, unfortunately, you can't, use that tool as a cheat. You got to actually, show all the work. But if you wanted to do it in your calculator, that is how you would work that situation. Okay? Now, if there wasn't a place where they swapped, if it just stayed top curve minus bottom curve the entire time, and you wouldn't need to worry about that, then you don't need to worry about the absolute value bars. You would just type it in like normal. Okay, so now, last thing, let's talk about when curves are defined by their y values instead of their x values. So now, find the area of the region bounded by the graphs of x equals 3 minus y squared and x equals y plus 1. All right, in this situation, okay, instead of going from top to bottom, now we're going to have to go from right to left. Okay, let's think about this. So let's go ahead and graph this. So I've got 3 minus y squared. That's going to be the quadratic. 1, 2, 3. Looks like this. Okay. X equals y plus 1. Well, that's your linear equation. So that's also, if you want to think about that as y is equal to x minus 1, you would graph that down here, slope of 1, boom, done. Okay, so we want the area bounded between so this right here. Okay, now up to this point, we've done everything in terms of x. Okay, we've done like when we say things in terms of x, we would do top curve minus bottom curve, but then you integrate in terms of x. It's not going to work that way because now we're doing everything in terms of y. Just like when we found the area in terms of y, which we have done before, okay? When we do things in terms of y, now instead of saying top minus bottom, we're going to say the rightmost curve minus the leftmost curve with respect to y. Okay, so remember when everything was in terms of x, we did top minus bottom, higher minus lower. Well, now your higher values for things in terms of y is the furthest to the right. So here my rightmost curve would be the quadratic minus my leftmost curve, which is the linear graph. Okay, but I also, like usual, I need to know from where to where. Now, the catch to this is I don't want my bounds in terms of x like I did before because I'm not doing things in terms of x. I'm doing everything in terms of y. I need to find my bounds in terms of y. So, find bounds. Again, just like we've done in the past, you set them equal to each other. 3 minus y squared. Where is that equal to y plus 1? Okay. I like positive y squared, so I'll move everything to the right here. Equals y squared plus y minus 2. So 0 equals y plus 2 and y minus 1. So y equals -2 and +1 are my bounds here. All right, so I've got from -2 to 1. Overall, the curve that is furthest to the right is the quadratic. So that's going to be 3 minus y squared. Minus the curve that is to the left, which is your linear curve. That is y plus 1 dy. Now I realize outside of the bounds, this curve is further to the right than this curve. However, just right here, like for example, if I were to erase all of these lines, boop, erase, 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 all this stuff. If I want to just this right here, okay, the rightmost curve is the quadratic, the leftmost curve is the linear. So that's why we say right minus left. And from here, it's a very simple, just basic integration using first fundamental theorem. Again, I'm going to skip over that because we know how to find the integral from here. The answer should be 9/2, but I have that worked out and we'll post that on Canvas for you guys as well. Okay? That is the area between two different curves. Again, as always, Prof. Rob Bob, Khan Academy, and CalcChat CalcView. This is 6.1 in your textbook if you need help using CalcChat or CalcView. Good luck!